Okay, this is 2.1, and 2.1 is about inductive reasoning and conjecture. And we also talk about counterexamples. So inductive reasoning is basically making a conclusion based on observations and patterns. So this happens almost daily when you in your science classes or biology research, medical research. So sometimes, for example, if you notice that some people catches a cold as soon as the temperature drops significantly when they don't wear enough clothes, that is a conclusion that you drew based on your observations. Somebody in your family must be always catching a cold when the temperature drops significantly when they don't wear enough clothes, right? So that conclusive statement is called a conjecture. So a conjecture is a concluding statement reached using inductive reasoning. And in math, we have many, many examples. So in the examples below, let's look at this. We have several numbers. We're supposed to find the next 5 terms of the sequences, then write a conjecture. So we have a sequence here. We have 38, 31, and then 24, 17. Notice that from the first number to the next number, what is the pattern, right? So it looks like if we just keep subtracting 7, we'll get to the same pattern. So we have -4, -11. The last one is -18. So all of these numbers from the 38 to the -18 is each term. So we can say to generate the next term, subtract 7 from, oops, that's a 7, from the previous term. So that is my conjecture. Okay, I observed the pattern that was given. I filled in the next 5 terms, and then I drew a concluding statement, which is called a conjecture. So let's look at the second example. I've got, oops, sorry. See if I can move that up. There we go. So I now have 2, 5, 11, 23. I think 2 and 5, and then that's 3. If 2 plus 3 is 5, 5 plus 3 is 8. So that is not the pattern. However, if I do 2 squared is 4, 4 plus 1 is 5. 5, that's not a square, so that doesn't work either. What if I do 2 times 2 is 4, 4 plus 1 is 5. 5 times 2 is 10, 10 plus 1 is 11. 11 times 2 is 22. That looks like the pattern. So if I do 23 times 2, I would have 46 plus 1 is 47. And if I keep the same pattern, 47 times 2 plus 1, that's 95. 95 times 2 is 190. 190 plus 1 is 191. And I would have 383, 767. So my conjecture is to generate the next term, double the previous term, double the previous term, and add 1. That's my conjecture, right? So I multiplied the previous term by 2 and then I added 1. That's what I did. So for number 3 actually those are very familiar numbers. 1, 4, 9, 16. They're all perfect squares. So that's 1 squared, 2 squared, 3 squared, 4 squared. Now I would have 5 squared, which is 25. 6 squared is 36. 7 squared is 49. Then 64 and 81. And the conjecture is each term is a perfect square. Each term is a square. To find, I can further elaborate, to find the nth term, square n. So if I want to find the 5th term, it's 5 squared. Okay. Let's look at number 4. A, D, G, J. I would say A to D, I have B, C. D to G is E, F. So it looks like in the alphabet, I just go from the first letter to the next letter by skipping 2 letters. So J, after J, I would skip 2. I would have M, O, P. Wait, A2, is this right? J, L, K, M. After M is O, P, Q, Q, R, S, T, T, U, V, W, X, Y, Z. That's what I would say, right? So this again is to generate the next term. To generate next term, skip 2 letters. After the previous term. You don't have to use the exact same words as I do, but oops, sorry about that. But it's not very that's a term. I'm going to cross that out. Okay, because it's a math problem, there are not that many other different ways of describing it, but more or less, as long as you make the statement precisely, and this statement cannot be read in any other way but to generate this pattern, then you're good. Okay, I think the next one is a silly one. 7:30, 7:25, 8:20. Obviously, you add 25 minutes to the previous time. We do this all the time in our life every day. So this really is just silly. Let's see, it will be 9:25, I think. No, I'm sorry, 9:35. And then it's 10 o'clock. If I add 25 minutes, then 10:25. So I'm not going to write it out. The conjecture here is to generate that next term, add 25 minutes to the previous term, right? And then the 6th example, I have 3, 1, 4, 1, 5. This is very random. 3, 1, 4, 1, 5. You know what? If I put this as a decimal point, I would have 3.1415, right? So this 3.14 is pi. So these are the digits in pi. You don't have to memorize this. This one is a little harder. So it's 3.141592653. See if you want to challenge yourself. One of my former students actually managed to memorize 100, up to 100th digit after the decimal point, which was really cool. We had a show and tell one day in class. So the conjecture here is each term is a digit of pi. To find the nth term, you have to find the nth digit of pi. So again, each term is a digit of pi. That's the conjecture here. So, okay, now, in the next one, in the next concept, we're going to talk about, let's see, we're going to talk about counterexamples. Counterexample is just like what it sounds. Whoops, sorry, I'm dropping my stuff. It's an example that shows a conjecture right? So some of you teenagers are familiar with this. When your parents give you some reasoning and ask you to do some things, you like to provide a counterexample, right? So let's see, what are some of these examples? Determine whether the conjecture is true or false. If false, provide a counterexample. The sum of any two consecutive integers is always odd. And so if I have, let's do some examples. So if I have 2 plus 3, that's 5. If I have 58 plus 59, that's 59. I would have 117. That's odd. So maybe 5 plus 6, can't write 6. 5 plus 6, I would have 11. It looks like this is true, right? So algebraically, we can also prove that if I have n and I have n plus 1, if I add them together, I would have 2n plus 1. 2n is always an even number, plus 1, I would make it odd. So this is true. There's no counterexample for this one. Next one, the product of two numbers is always larger than either number. Be very careful. Here it says two numbers, so I would say this is false, because I know as a math teacher I can provide some counterexamples. So let's say 2 times a half equals 1. That 1 is less than 2, right? And what else? Product of two numbers. All the odd things always seems to happen with 0 or 1. So 0 times 25, I would have 0 rather than a number that's greater than 0 and greater than 25. So this one is definitely false. The third one, the product of two perfect squares is always a perfect square. I know that's true. The fourth one, the area of a rectangle is 6 square meters. Then the dimension must be 2 meters by 3 meters. That is not true. That's a false. So the counterexample is, how about a 1 meter times 6 meters? That also gives me 6 square meters, right? So number 5, dividing 2 always produce a number less than the original number. So number 5 is also false. Counterexample, I would do negative 8 divided by 2 equals negative 4, right? Number 6, vertical angles are never complementary angles. Remember, complementary angles, the way I remember it is the C makes a corner, so that's 90 degrees. Vertical angles are never complementary angles. This one is false. So the counterexample is that if the angles are 45 degrees, then they are complementary. Then they are complementary angles. So that's one example. And now I'm going to move my sheet up. Okay. So here, number 7, if a times b equals to 0, then either a equals 0 or b equals 0. This we know is true. This is one of the theorems that we have learned. Number 8, two angles are supplementary to the same angle must be congruent. I would say this is true, and you can raise plenty of examples. So if my angle A plus, let's say, 135 degrees is my second angle, and they equal 180 degrees, right? Supplementary. And then angle A must be 45 degrees. And if I make the second assumption, angle B, measure of angle B plus the same angle is still supplementary, then I can draw the conclusion that the angle B is also 45 degrees. I can go on and on and on like this forever and never stop, right? So let's look at number 9. All state names have at least 2 syllables. Number 9, I don't know. Is that true? I think Maine only has 1, right? Number 10, squaring a number and adding 1 will always produce an even number. This, in going back to our previous example, is always false, because if you square a number, say 10, you add another 1, you give an odd number, right? So if you square, say, 3, 3 times 3 is 9. 9 plus 1, that's 10. That's an even number. But if you square a even number, say 4, 4 squared plus 1 gives you 17. These are counter examples. Here are some additional practices. I'm going to leave these with you. You can find plenty of counter examples, write your own conjecture, and work with a partner on this. And I'll see you in class. We'll probably do some of this in class then. Okay? Thanks, guys. This is 2.1.